In this packet, you will find abbreviated notes for topics 17 and 18, talking about probability, but you need to be aware that you will probably need to fill in some gaps by watching the digits programs, and these notes actually start with 17.2, so I have assigned 17.1 for you to watch, and then assignment 17.1 for homework. So with 17.2, we talk about some important vocabulary. An action is a process with an uncertain result when we're talking about probability. So it's a process with an uncertain result. An outcome is a possible result of an action. So if my action is flipping a coin, I don't know what the result will be, but my outcomes are the coin landing on heads or the coin landing on tails. My sample space is the set of all possible outcomes. And my sample space for flipping a coin is heads and tails. An event is a single outcome or a group of outcomes. So the event would be flipping a heads, or another event would be flipping a tails. So in this next part, these 6 different things, you're identifying if each is an action, a sample space, or an event. So I would like for you to pause the video. Once you have completed the 6, resume the video to find out if you were correct. Pause the video now, please. So you should have come up with 1 and 2 being actions, 3 and 4 are sample spaces, and 5 and 6 are events. So that's a very brief overlook of section 17.2. I'm going to move on to section 17.3. Again, these are very abbreviated notes, so you will probably need to watch the videos on digits to help fill in some gaps. Section 17.3 talks about relative frequency and experimental probability. And those two are actually the same thing. The relative frequency is the number of times an event occurs divided by the total number of trials. And again, relative frequency and experimental probability mean the same thing. So you find the experimental probability or relative frequency by dividing the number of times an event occurs by the total number of trials done. Make sure that you are familiar with this notation. P parentheses event means the probability of the event happening. This next sentence with the asterisk is obviously very important. The more trials you have in an experiment, the closer the experimental probability will be to the theoretical probability. And section 17.4 talks about theoretical probability. So theoretical probability is the number of favorable outcomes divided by the number of possible outcomes. So you may be wondering what the difference is, and favorable outcomes are what the event is. So if I'm talking about the probability of heads, I would count how many heads were the outcomes, divide that by the total possible outcomes. So on a coin there's 1 head, so that's a favorable outcome, 1, and the possible outcomes is heads or tails, so that would be 2, so the probability of getting a heads on one coin flip is 1/2. That's theoretical probability. When you do experimental probability, you actually perform an experiment and record the data and then base the probability on your data from the experiment. So let's take a look at this next part. State whether each is an example of experimental probability or theoretical probability. So again, it's in the name, but experimental probability is based on an actual experiment completed. Theoretical probability is purely based on numbers. What should happen, what you would expect to happen based on the pure numbers. So number 1, a soccer player took 12 shots on goal and scored once, so the probability of a goal is 1/12. So I would say since that actually happened, it is experimental probability. You roll a standard number cube, which we call a die, 50 times and get 8 threes. So the probability of rolling a 3 is 8/50ths, which is 16%. So that's based on what actually happened in an experiment, so that's experimental probability. The theoretical probability of rolling a 3 on a number cube is 1/6. So it's pretty close to that experimental probability. Number 3, you choose one tulip at random from a vase that has 5 red tulips and 7 yellow tulips. So the probability of red is 5/12. So it does not give you information about what you actually chose. So based on just the pure numbers, the probability is 5 out of 12, and therefore that is theoretical probability. If you need any explanation, please see me about that. Alright, let's move on to what a simulation is. A simulation is a model used to find probabilities. And we can use coins or dice or spinners, and you have seen me use the calculator to generate numbers. We can use one of those to simulate probability situations. And I will teach you how to do that. We will assign each outcome in the sample space to one outcome of the tool you're using, and then simulate the situation using multiple trials. So we will do lots of practice with that. Let's take a look at the next problem. It says that I choose one person at random to take the recycling to the bin, and suppose the recycling is taken out 32 times a year. What's the theoretical probability that I will choose a girl from our class? So the first thing you need to know is that there are 14 girls in the class and 29 total students. So in our first period class, there are 14 girls and 29 students. So theoretically, I should choose a girl 14 out of 29 times. If I calculate the percent, I would do 14 divided by 29, and I get approximately 48%. I'm going to round to the nearest percent. So that's about 48% of the time I would choose a girl. So if I'm doing this 32 times a year, I would take that probability, 48%, and multiply it by 32 times, and that would be how many times I would expect to pick a girl. So 0.48 times 32, and you get excuse me, 15.36. So I would expect to choose a girl about 15 times. Now, what I'm going to do is I'm going to run a simulation of the situation having 32 trials and I'm going to record my results. Okay, so I have 14 girls in the class, 29 students are in the class, which means I must have 15 boys in the class. So what I'm going to do is I'm going to use my calculator to randomly generate numbers from 1 to 29 because I have 29 students. And I'm going to assign numbers 1 through 14 to be girls. And I'm going to assign 15 through 29 to be boys. So anytime a number from 1 to 14 is generated, that means I picked a girl. If I get numbers 15 to 29, that means I will have chosen a boy. I'm going to run 32 trials because that's how many times I am picking somebody to take the recycle bin down. Alright, so to do this, we are going to use our calculators. I am using the TI-30X2S, but you can use your multi-view, and it's the same way. So I am going to have it pick a number from 1 to 29, and this is how we do this. So you should look at your calculator, and this button here says PRB, that stands for probability. So you're going to select probability, and you see NPR, NCR, and an exclamation point. Then I need you to arrow over several times until you see RANDI. So that's random, and the I stands for integer. I don't want any decimals in my answer or in my numbers, so random integer is what I'm choosing. So once you select that by hitting enter, you should see RANDI and then a parentheses. With those parentheses, you're going to put the numbers that are in your range from 1 to 29. So on your calculator, you should see RANDI parentheses. You are going to type in the number 1. That's the first number. Then to get the comma, you are going to select your second button, and then above the parentheses, the closed parentheses is a comma. So you're going to select that to get your comma. And then the largest number you want to have shown is 29 because there are 29 students here. Then make sure that you close the parentheses. If you forget to do that, then it will give you an error. So close the parentheses, and then once you hit enter, it will give you a number anywhere from 1 to 29. In my case, I just did this, and my first number is 7. So I'm going to continue to hit enter. Gives me another number, 18. And I repeat this 32 times. So I would like for you to complete this on your own, come up with your own 32 numbers using your calculator to get used to it, and then we will move on. So pause the video and come up with your 32 numbers on your calculator. Okay, these are the results of my 32 trials. So now what I'm going to do is I'm going to identify which ones are girls. So I'm going to circle the ones that are numbers 1 through 14. Oops, sorry about that. So I'm circling all the numbers 1 to 14, so you should do that with your papers. Remember, the numbers 1 through 14 represented the girls in the class. Alright, so I believe I've circled all of my numbers 1 through 14, and now I'm going to count how many girls I chose. So in my randomly generated information, I got 13 out of 32 girls picked, which is 41%. Now if we compare that to what was expected, based on theoretical probability, which was 48%, we can see that the experimental probability was a little bit lower than that. So we got 13 out of 32, which was approximately 41%. Now, you should have generated your own numbers, so your numbers would be different from mine, most likely. So how does that compare to the theoretical? The experimental was about 7% less likely to pick girls. So I said that the experimental probability was about 7% lower. All right, now we are moving on to the next section, which is section 17.5, and it talks about probability models. And a probability model is an action, its sample space, and a list of events with their probabilities. So that entire thing would be a probability model. So again, a probability model is an action, its sample space, and a list of the events with their probabilities. Two things we must have in order for it to be a probability model. And the first one is that each outcome is in exactly one event. And the second is that the sum of the probabilities must be 1. So again, the characteristics of a probability model are that each outcome is in exactly one event, and the sum of the probabilities has to equal 1. In a uniform probability model, each probability is equally likely to happen. So each outcome is equally likely to happen. So it uses theoretical probability of equally likely outcomes. Uniform probability model uses theoretical probability of equally likely outcomes. Let's take a look at these scenarios. And the question is, can you use theoretical probability or should you collect data to use relative frequencies? Number 1 says a city planner, and there are a lot of typos in here, I apologize. A city planner wants to know the probability that a car waiting at a stop sign will turn left, go straight, or turn right. So, if we're talking about theoretical probability, they would have 1/3 of the time going left, 1/3 of the time going straight, and 1/3 of the time going right. But does that actually happen in a city? So, in order to know what actually happens, you would want to collect data and use relative frequencies. So we're going to select that we should collect data here. Number 2, two friends walk on a walk, excuse me, are playing a game. At each intersection, they choose at random from 3 slips of paper. Turn left, go straight, or turn right. What's the probability they will turn left, go straight, or turn right? So here, since they're picking slips out of a paper to make their decisions, it really does not need to have data collected for it. So this is theoretical probability. The third one, a cashier at a grocery store asks a customer, what type of bag would you like? Plastic, paper, or use your own reusable bag? So in this one, if you are the person in charge of inventory for bags, you would definitely want to collect data to see if the majority of your customers use reusable bags or if they like plastic or paper. So we would want to collect data for that one. All right. This next example is going to take a significant amount of time for you to complete. This is beginning 17.6 here. And the example is when you reach a 5-way maze on a computer game, the game chooses one path at random for you to go down. Use a random number generator to simulate 250 times what happens when you reach this point in the game. How do your results compare with what a uniform probability model of this situation predicts? So let's first talk about the uniform probability model of this situation. So if you take a look, there are 5 paths you could go through, and 2 of them are dead ends. 2 of them go back to start, and 1 of them wins. So according to theoretical probability and a uniform probability model saying that each of those paths is equally likely, you would have a probability of 40% when you lose, 40% to start back at the beginning, and 20% chance of winning. What we're going to do, or what you're going to do on your own, is simulate 250 games and see what happens when you reach this point in the game. So what you want to do is assign each outcome a number 1 through 5. So I will say 1, 2, 3, 4, and 5. And I'm going to have my random number generator on my calculator randomly pick numbers 1 through 5. So it's going to be rand I for random integer, parentheses 1, 5. And then I'm going to run 250 trials. So there are 3 options that can happen. So I'm going to make a table of the 3 options. The first option is losing at a dead end. The second option is starting over. And the third option is winning. So when I randomly generate numbers, if it's a 1 or a 3, I would I would put a tick mark in the losing column. If it's a 2 or a 4, I would put a mark in start over. And if it's 5, then I would put a tick mark in the win column. So you're going to end up with 250 tick marks. So complete that. It'll take some time. Complete that example there and see what the probability is compared to the uniform probability model. And this takes us to the end of topic 7 in this notes packet. So I will make a separate video for topic 18 material.